Now we're going to look at the atmospheric layers based on temperature characteristics. Now we're going to focus in on the atmospheric layers in that red line that's on this image. If we look at the red line, it goes back and forth. It goes to the left, and then to the right, and to the left, and to the right as it works its way up. That red line, what that illustrates is temperature, and the closer we are to the left-hand side, the cooler the temperature, and whereas we go closer to the right-hand side, the warmer, the hotter the temperature. So if you can think about this, what we would always thought, if you go to the top of a mountain, it's going to be cooler. And so scientists and people who theorize this all the way up until just a few hundred years ago assumed that the further you were away from Earth's surface, the cooler it was. However, as we started sending balloons up into the sky, weather balloons up into the sky to identify temperature at different layers, you found this different pattern where actually in certain areas the temperature goes up, and then in other areas it goes back down. And so these are kind of relatively newer ideas over the last 100 or so years, understanding the different layers based on temperature. Just always assumed the higher you would go up, the cooler it would be. Let's focus first in on the thermosphere. The thermosphere is anywhere from 50 to about 300 miles above Earth's surface, and that whole about 300 miles is the fact that it swells and contracts based on the amount of solar energy. Not going to go too much further into that. Also, if you look, this overlaps with the heterosphere from the previous image, so the heterosphere and the thermosphere overlap with each other. In terms of the mass of the atmosphere, most of the mass of the atmosphere is found below the thermosphere, so it's not found up in this upper level of the atmosphere. Thermosphere is also referred to as the heat sphere. This is where you're going to find the highest temperature in Earth's atmosphere. It's going to be found up at the top of the thermosphere. The thermosphere temperatures, one thing is, increases rapidly with altitude. So in the thermosphere, key characteristic, as you go up, temperature also goes up. Why is temperature so high here? What's going on here? Keep in mind those gamma and X-rays, those short wave, those ones with the highest energy, start to interact and become absorbed by those hydrogen, helium, and nitrogen gas and oxygen gases up in the, if we go back to the heterosphere. So you have the interaction of short wave sun rays, the short wave of the electromagnetic spectrum interacting with these upper level atoms produces a lot of heat energy. And so a byproduct of that absorption is the production of heat energy. We'll come back and talk more about this on the following slide. There's a good chance that this slide will get screwed up as I send it up to YouTube, but let's see if it works. And so we return to, remember, our heterosphere. We have these different layers. And so this is also, the thermosphere overlaps with the heterosphere. And so we have these different layers based on atomic mass. And so what these arrows illustrate here are those incoming shortwave, high energy. Keep in mind there's also long wave, but the shortwave ones, they start to get filtered out here. They start to get filtered out in this upper level of the atmosphere. And so part of that filtering process is they interact with these upper level atoms. And when they interact with them, the atoms absorb and essentially filter out that shortwave radiation, and a byproduct of that is heat. And because we're going to have more reactions happening at the top, when those interactions first occur, you're going to have a warmer temperature up at the upper level of the thermosphere. Whereas as you go further down, there's less likelihood of that shortwave radiation reaching the lower levels, reaching the helium, nitrogen, and oxygen, and so thus less heat reactions occurring. I'm just bringing this back to kind of refresh us as far as gamma rays, X-rays, shortwave, high energy, and all of that. So in the previous slide, what I'm referring to, gamma rays and X-rays, those are the shortwave, the high energy rays that are filtered out in this upper level of the atmosphere, in the thermosphere. One of the things we're going to see with each of these spheres or layers based on temperature there's a specific barrier, a specific line that denotes the change from one sphere, one layer to the next based on temperature. And so the first one is called the thermopause. And the thermopause is the top of the thermosphere. And so once again, that's going to be 300 miles above Earth's surface. Just below the thermosphere is the mesosphere. If we look at the red line now, you can see the red line illustrates a pattern in which, as we go up, temperature goes down. So unlike the thermosphere, where as we go up, temperature goes up, mesosphere, as we go up, temperature goes down. 31 to 50 miles above Earth's surface is the mesosphere, also known as Earth's middle atmosphere. One of the characteristics, like I've just said, is temperature decreases with increasing altitude. One characteristic of the mesosphere is there's no particular properties, there's no particular atoms and reactions occurring here, and so there's none of those wavelengths of long wave, short wave being intercepted here in this area. So there's none of those heat reactions I mentioned in the thermosphere. At the top of the top of the mesosphere, we find the mesopause. The mesopause also, we could say, is at the bottom of the thermosphere. So the mesopause denotes a change between the mesosphere and the thermosphere. The mesopause being the top of the mesosphere. The mesopause would be the coldest part of Earth's atmosphere. And so the coldest part of Earth's atmosphere is the mesopause. And once again, these pauses denote a temperature change. And so below, temperature decreases with altitude. Above the mesopause, temperature increases with altitude. One characteristic of the mesosphere is the presence of the mesospheric clouds. And these mesospheric clouds, very difficult to see, but these aren't the types of clouds that we see every day. And so these clouds, of course, are at a much higher altitude than the clouds in the weather that occurs each day here in Indiana. These particular clouds have a specific name. They're called noctilucent clouds or polar mesospheric clouds. And essentially what happens here is, once again, keeping in mind that this area is the coldest part of the atmosphere, we've got all kinds of dust and debris that's coming hurling at Earth as we speak. And so think of it as a bunch of meteors. And over time, these meteors in the upper atmosphere, they start to break down. And so eventually all that dust, all that meteoric dust collects. Because this is very much the coldest part of the atmosphere, ice crystals then develop on that dust. And so once again, if you get the perfect sunlight situation, very low sunlight, so in the evening, and you're up close to the poles, you can actually view these ice crystals being illuminated by the sun. But these are very rarely spotted, like I've said before. And you can see these noctilucent clouds found at the top there of the mesosphere. That's what the white hazy area is representing. Next up, just below the mesosphere is the stratosphere, where temperature, once again, a lot like the thermosphere, goes up as we increase in terms of altitude. About 11 to 31 miles above Earth's surface is where we would find the stratosphere, where temperature increases with altitude. Why does it increase with altitude? In the top of the stratosphere, you find a higher presence or higher quantity of ozone gas molecules. And so keeping in mind what we've talked about beforehand, the X-rays and the gamma rays, they've been filtered out in a higher level. Now all we have left is the infrared visible light and UV rays. Well, in the stratosphere, we have those UV rays starting to have reactions with the ozone gas molecules at the top level, thus producing, once again, a byproduct, heat energy. At the top of the stratosphere is the stratopause, and so once again the stratopause is going to denote a change in temperature, whereas below the stratosphere temperature increases with altitude, above the mesosphere temperature decreases with altitude. And so we find this temperature change occurring at the stratopause. The higher temperatures found in this region of the atmosphere, the stratosphere, occurs because of a localized concentration of ozone gas molecules. And so we can think of these ozone gas molecules being showcased by orange. So there's more orange at the top of the stratosphere. And so these molecules, one of the things they do is they absorb ultraviolet sunlight, creating heat energy. Same way we saw in the thermosphere. So this helps to warm the stratosphere. And so this ozone, which is just found pretty much in this layer, helps to filter out a lot of those harmful UV rays and protects them from reaching us down at Earth's surface. And so without the ozone layer, without this thin level of ozone, life would not exist on Earth's surface as we know it. Returning now to our electromagnetic spectrum image, we've talked about beforehand the X-rays and gamma rays. They've been filtered out, and so now the ultraviolet rays. So another way to illustrate what I was talking about beforehand, just in case, who knows how this is going to get screwed up when I send it up to YouTube, but I'm trying to illustrate the fact that those ultraviolet rays are filtered at the top level of the stratosphere, and so once again there's less UV rays making it to the bottom, and thus less interactions with ozone, which is also found in less quantities at the bottom of the stratosphere, causes less heat energy, less reactions, and cooler temperatures at the bottom of the stratosphere. Our fourth and final layer based on temperature is the troposphere, and so we tropes around the troposphere, us human beings. The troposphere is anywhere from 0 to 11 miles above Earth's surface. And if we go to the poles, it's 0 to 6 miles where we are about 0 to 8 miles, and the thickness would be about 0 to 11 miles above the equator. And overwhelmingly, this is where most of the mass of Earth's atmosphere is. And so we think about the density of the atmosphere. Overwhelmingly, much of the mass of the atmosphere we can find in the troposphere. It's the thickest and most dense level of the atmosphere. And it contains the biosphere. And so at the end of the semester, I finally get to talk about living things. And we'll talk about the role of living things in the troposphere. And so we'll focus mostly on the troposphere as we move forward. And so overwhelmingly, this is where our weather occurs. And so our weather, if we think about the tallest cloud in the sky, very rarely do we find a cloud poking above the troposphere, poking above the tropopause, which is once again going to be the top layer, the top top of the troposphere. In 1960, Joseph Kittinger decided to go up into a balloon, up into the top level, about halfway up the stratosphere, and decided to jump. And so as he began to fall, one of the characteristics is he heard nothing. He didn't hear his jacket fluttering in the wind, because the air is so thin here. There was nothing to create any friction against the cloth of his jacket as he fell down. So he heard nothing. And so he could see no rippling in his jacket, he could hear nothing, but he was falling at 614 miles per hour. But one of the things is because the air is denser, the closer you get to the surface, he actually started to slow down. And so he actually started to slow down to terminal velocity, whatever terminal velocity is, somewhere in the hundreds miles per hour. So naturally, before even throwing his parachute, he naturally slowed down just because the air is thicker here. Which I use this to emphasize the kind of the role as far as the density of air. The mass of the Earth's atmosphere is greater the closer you get to Earth's surface. Here in the troposphere, temperature decreases with altitude. We know this if we go up a mountain, if we go up in a plane, or if we go up in a hot air balloon, then it gets cooler as we increase our elevation. And in characteristic, I've talked about on a previous slide, is the fact that the troposphere is actually thickest between the tropics, about half as thick there at the poles. At the top of the troposphere, we have what we call the tropopause. And the tropopause, once again, is going to denote a temperature change between one layer, one sphere, and another. Key to understanding the tropopause is actually a degree Fahrenheit. So it's a little bit less of a specific mile above Earth's surface, but it's more to that point above Earth's surface that we reach negative 7 degrees Fahrenheit. So negative 7 degrees Fahrenheit, once we reach that point, we are now at the tropopause. And so this is very important to kind of understand why also we find this different thickness between the poles and the tropics. Just think of it like this. If I'm at the poles, for me to go up to reach negative 70 degrees Fahrenheit won't take as long. It's already really cold there to begin with. Whereas at the tropics along the equator, where it's on average 80 degrees Fahrenheit every single day, for me to go from 80 degrees Fahrenheit on the surface all the way up to a point that's negative 70 degrees Fahrenheit, I'm going to have to go further up than I am over the poles. The tropopause very much acts as a lid, and so that's why our weather overwhelmingly is contained in the troposphere. It's held down below by the tropopause, and it prevents that dense cool air from mixing with the less dense warm air above found there in the troposphere. And so once again, the tropopause denotes a temperature inversion, and so in the troposphere, temperature decreases with altitude, whereas in the stratosphere, temperature once again increases with altitude.